Okay, so we are going to start looking at parent functions today. On that test review I gave you, parent functions are not on the test review, but the sketching part of them will be, and I will explain to you once we're done talking today all that I'm going to expect from you on the test on Friday. Obviously, I will expect a whole lot more later on, but parent functions overall are not new to you. This first one, we start with part 1. This is going on page 21 when we're done. I didn't put a little space for it, but you can write it up there so you know where it goes. Parent functions overall are not new to you. Most all of these, and I know not every single one of them, but most of these you have seen either in Algebra 1 or in Algebra 1 and Geometry, or in Algebra 1, Geometry, and Algebra 2. You should have at least seen them and been exposed to them. I know y'all do little parent function booklets and stuff like that. Knowing certain things about these, super important, okay? And I can help you understand it in a very easy way, but you have to know the shape of them, and you have to know what I call anchor points. I don't think they have a real name, but I think that they are invaluable when you are doing these. So we're going to abbreviate it AP, so at the top you might want to write AP means anchor points, because again, it's kind of like a term that I made up. It's not necessarily anything you've heard before. I don't think it has a real term. So we're going to talk about anchor points for each one. So you need to know the shape and the anchor points. And if you can do that, you can transform any of these. It's all a piece of cake. The problem comes in when you don't even know where the anchor points are and you don't know what the function is. That's a problem. Bless you. Especially the ones on the front here. Yes, these are way old business. I'm not going to go through every single one of these with you. I'm going to work out all of one of them and maybe another one just so that you know what is expected of you inside of these blanks and how to answer the question. And then we're going to talk about the anchor points for all of them and a couple other little things. But the rest of it, you're going to go back in and fill in. So for the linear, well, first of all, it says a function family is a group of functions with similar characteristics. The parent function is the simplest of the functions in a family. You must be able to recognize each of these functions along with their characteristics. You have to, or you basically have no hope. I mean, that's just the way that it is. So for the linear, our parent function, meaning what is the equation for it? F of x equals what? X. Okay? F of x equals x. That's an Algebra 1 thing. So then we have anchor points, meaning that it's a line, so you only need 2 points to make a line. But the anchor points are going to have anywhere from 3 to 5 for each function that we do, so that you know where to start when we do the transformations. And so here are the 3 for the linear. Okay, so I want to mark them, and then we're going to write them out here. Our anchor points, make a little XY chart here, are going to be -1, 0, 0, and 1, 1. Honestly, the transformations with a line, we would probably do it differently anyway, but we're just going to do this for every single one of them. So what is the domain here? We're going to write domain and range in interval notation every time. So what's the domain? Negative infinity to infinity, right? Negative infinity to infinity. And your infinities are always open, so it's an open interval. What's the range? Negative infinity to infinity. Good. Now, when it says x-intercept, how do you have to write your answer? Ordered pairs. Some of us did not do that on that quiz, and we got things mixed up. And that's why I'm giving them back to you. What do you want to make sure we're not making the same? And so, here, 0, 0. If I ask you for zeros, root solutions, anything else, that's when it's in set notation. What's our y-intercept? 0, 0. Now, extrema, I meant to change that to critical points because if I have a point of inflection, which I don't here, but I want that included there too. So if you come across a point of inflection, it's not an extrema, but just write it in there with it. Do I have any extrema on this graph? No, I do not. So there's just none. What are my increasing intervals? Negative infinity to infinity, right? And your increasing and decreasing intervals are always open intervals with parentheses, not closed with brackets, no matter whether it's infinity or not. Decreasing intervals? None. Okay? Then the end behavior, like what you just had on that quiz, we have to write out the little thing here. As x approaches infinity, f of x approaches what? Infinity. As x gets really big, y gets really big. And we'll do a little semicolon, and then as x approaches negative infinity, f of x approaches negative infinity. Okay. Everybody okay with that? Do we have any discontinuities? No, so it's none. Is it even or odd? Or neither. Even, odd, or neither. It could be neither. Odd. Even means I would have symmetry with respect to the y-axis, which I don't if I reflect it in the y-axis. Odd means it has point symmetry. I'm in quadrants 1 and 3. If you rotate your paper 180 degrees, you're in quadrants 1 and 3. You have to pretend like it's right side up then. So this is odd. So then we have to show that. I find f of negative x, or if you're not sure, you can just do this and it would tell you anyway. F of negative x equals negative x, right? That means that is negative f of x, and that is what makes it odd. Okay. Everybody okay with that? We good? All right. Absolute value, not new, right? So f of x is equal to what? Absolute value of x. That's why it's called the absolute value function, right? All right, so for the absolute value function, our anchor points are just these three. Since we know it's like a broken line. I don't know if you've ever thought about that before, but if I take f of x, this f of x equals x is this right here. But then when I take the absolute value, basically I just bend it here and reflect that part up. So it's kind of, it's still part linear, I guess. So I don't need more than these two to be able to continue that on. So for my anchor points here, I have negative 1, 1, 0, 0, and 1, 1. Everybody okay with that? And then, like I said, later on you're going to go back and fill in the rest. We're just going to talk about each function and their anchor points so that it's not a guessing game. All right, quadratic. My parent function would be f of x equals what? X squared. So these three are for sure anchor points. However, that's the same three I just used for the absolute value. And so if I don't have more than that, I don't necessarily know how my curve needs to go. So I also need 2, 4, and negative 2, 4. So here I'm going to have 5 of them. Right? So my anchor points, x, y, it's going to give me negative 2, 4, negative 1, 1, 0, 0, 1, 1, and 2, 4. What questions do you have right now? Anything? We're good? Okay, awesome. And now, wish. But if you wish for that, trust me, it becomes like 80 degrees in here, and then it's miserable, and you're just sitting there sweating and can't think. It's terrible. It's one or the other. All right, parent function. This one is cubic. This is not new either. So f of x is equal to x cubed, right? So these 3 points here for sure are some of our anchor points. But again, those are the 3 I use for the line. So I got to have something else so I can make sure I get the right curve and I'm going in the right directions here. So the other 2 I'm going to use are not even on there. So if I'm at positive 2, what would my y value be? 8. It's way up there. And negative 2, I'd be at negative 8. So my anchor points here, x, y, I'm going to start with negative 2, 8, negative 1, 1, negative 1, sorry. Negative 1, negative 1, duh. Negative 8. Yeah, see, that's where I started throwing myself off. Thank you. Negative 2, negative 8. Thank you. Negative 1, 0, 0, 1, 1, and 2, 8. Which, when I tell you you have to know these anchor points, it's not about going home and memorizing numbers. It should be kind of obvious if you understand how a cubic works. Like you can come up with them pretty quickly. But we don't need 1,000 points. 5 of them are important though to be able to get what we need, and I'll show you how that makes that easy. Now on this one, remember it's not an extrema, right? But it is a critical point. I have what is this point called? Point of inflection. And it is a point of inflection. Some people put just inflection on the quiz, and that does not make any sense. It's a point of inflection. Extrema are your max and mins. Critical points are points of inflections and maximums and minimums. So extrema just doesn't include the point of inflection. It's the maximums and minimums. So I should have put critical points there and not extrema, but because it includes that. So yeah, if I had a relative max, relative min, that's what would go there too. All right, square isn't brand new either, right? So f of x is equal to square root of x, and not plus or minus, okay? Just square root of x. So I have 3 anchor points here. So my anchor points are 1, 1, and 4, 2. So let's talk about one other thing here, our end behavior. Okay, we're going to do end behavior for this. As x approaches infinity, f of x approaches what? Infinity, right? What about as x approaches negative infinity? It doesn't. So since x doesn't approach infinity, there's not even anything to put here, okay? That's going to happen a couple of times. So, and it's kind of weird because we're talking about it as end behavior, not limits, that sort of thing. But we only have really half of it to write because it doesn't even approach it. So if it doesn't approach one or the other, then you only write basically half of the statements, okay? All right, let's look at cube root. Is this new? No. F of x is, by the way, when I ask you those questions, a lot of times I already know the answer, so it doesn't do you any good to lie. So I'm going to use these same 3 points here that I used even for the cubic. But again, I use those for a few things, so I got to have a couple more, and they go off the graph as well. So if I come way out here to -8, what would my y value be? -2, okay? So my anchor points here are going to be -8, -2, -1, -1, 0, 0, 1, 1, and 8, 2. So tell me how the cube root and the cubic functions are related to each other. What's the word for it? They're what? Well, they're reflected. Well, they both have origin symmetry. They're reflected they're actually reflected in the line y equals x. Like if I flip it over that line, okay? And then if you look at this little table we just made, they're inverses, because that's what happens. When you have an inverse, it reflects over the line y equals x, and the x and y values exchange places, right? So they're inverses of each other. All right. Next, I guess we're on the next piece of paper, right? So this is going on page 22. Reciprocal function. What does this function have that's not on the graph? Asymptotes. So we're going to sketch in our asymptotes, like so. So the asymptotes they're connected to the anchor points. They're not points, but whenever we look at the anchor points and I tell you what I want you to do with them, the asymptotes have to go with that too. It's going to really help you get these graphs in there right if you think about all the asymptote stuff first. So then the good news here, well, our function, first of all, is f of x equals 1 over x. This is a reciprocal. Your anchor points, you really only have 2, but it's 2 plus the asymptotes. There will be times where you may feel like you need to find another point just so you can get the graph, but we'll talk about that when we get there. But these are like the must-haves here. So our anchor points are just -1, -1, and 1, 1. Then when you know it's a reciprocal and you can get the asymptotes in there, then you're able to sketch in the rest of it. We good? All right, next one. Exponential. So with the exponential and the log graphs, when you have a parent function, you have to use a number or you can't write it. And so the number could be anything, even for the parent function. This graph in particular is using 2. So our function, our f of x, is going to be 2 to the x power. But it could be 5 to the x, 10 to the x, 1,000,000 to the x, and still have this basic same shape, but a few things change. Is there an asymptote on this graph? Yes, it's an exponential, so there's no way for me to get a negative y. 2 to any power, I can get a really small number. I can't make it become negative all of a sudden. So I have an asymptote here. And then I have 3 anchor points. This one's the most important one. 0, 1 is an anchor point regardless of what that base number is. If it's 5 to the x, 10 to the x, 2 to the x, whatever, 0, 1 is an anchor point. Because any of those numbers taken to the 0 power is going to give me 1. Make sense? And then this would just be faster or slower depending. So because this is 2, then when I'm at 1, I'm at 2. And when I'm at negative 1, I'm at 1/2. So my anchor points, x, y, I'm at negative 1, 1/2, 0, 1, and 1, 2. So these 2 right here, these change depending on the base. So if it was 5 to the x, I'd have negative 1 and 1, 5. But 0, 1 would still be one of them. Okay? Good? All right, here's another exponential. Exponentially increasing. This one is exponentially decreasing. So what changes with this? Do you know? Well, whenever x is our reciprocal, it's still an exponential, so I'm still going to have x in the exponent. What happens is when you have exponentially increasing, your base is greater than 1. If it is exponentially decreasing, it is less than 1 but greater than 0. So f of x would be equal to 1/2 to the x power. And that 1/2 has to be in parentheses, because if you don't put it in parentheses, it's going to look like 1 to the x power over 2, which is just 1/2. Okay, so make sure that if you have a fraction, it's in parentheses. And this is just a reflection, right? So I have an asymptote right here. And then my anchor points are these 3. I have negative 1, 2, because if I take 1/2 to the negative 1 power, right, it's going to give me the reciprocal of it. So it's negative 1, 2. This is still 0, 1 every time, regardless of the base. And then 1, 1/2. And once again, these 2 change depending on the base. Okay, it won't always be 2. All right, what questions do you have? We good? Awesome. All right, on the back of this one then. Okay, good pass. Okay, thank you. There you go. And then make sure you grab all 3 of those. So we have logs. Do I have an asymptote here? Yes. Where's the asymptote? Right there. The y-axis. What's that line? X equals 0. Good. Vertical. X equals 0. So for your logs, and the logs and the exponentials are reflections of each other. Not reflections, I'm sorry. They're inverses of each other. So they're reflected in the line y equals x. My anchor points here. Instead of 0, 1, I have 1, 0. Okay? And then if I write this out, f of x is equal to just the log of x. If that's all I write, what's the base? 10. Okay? So my anchor points here, then, I have this one where y is negative 1, and then I have another one that's way off of that. But because the base is 10 here, my anchor points, my first one, when y is negative 1, this is going to be at 1/10. And then I'm going to be at 1, 0, and then I will have 10, 1. And once again, these change depending on base. Okay? Does that make sense? Any questions? All right, so we got another log down here. They're reflections of each other. What do you think is going to be different between these 2 equations? The bases, just like this is where for exponentials. So f of x is equal to log, and this time, so for the first one up there that we just did, it's going to have that same shape and everything if the base of the log is greater than 1. If it's between 0 and 1, it's going to look like this. So this is 1/10. x. But again, that 1/10 could change to anything else. So I still have this asymptote here. I still have the anchor point of 1, 0. And then this one and another one that's off of there. So my anchor points are, this is going to be at 1/10, 1, 1, 0, and 10, negative 1. What questions do you have? Okay. Look at this last one. Have you seen this one before? No. So this is a, yes, where have you seen it? You want to explain it to us? Okay. All right, so this is called a Signum function. It's also can be called a sine function, but that can be confusing with like SIGN and SINE, so Signum is really probably more of what you're going to hear. It can be written a couple of different ways. We're going to look at it. We're going to graph it. It's actually very easy to graph. We're not going to do a whole bunch of transformations with it, but I want you to be exposed to it. It's something that Mr. Ackerman said, hey, instead of this other one that's usually in the mix of things, have them do this one. Because this is something you will work with in calculus a lot, but at least if you've actually seen it now and we can talk about some things about the graph, then when you get there, it just won't be brand new. But I don't want this one to stress you out. Okay, so even right now when we're going through it, like don't let this one overall stress you out. If everything else makes sense and this one confuses you, it's not the end of the world. Okay, so what this function looks like is f of x is equal to the absolute value of x divided by x, where x cannot equal 0 because we can't divide by 0. I say that, but then there's a point here. Okay, because sometimes it's graphed with a point there, sometimes it's not, and I'll show you a different way to write the function here. But basically, you substitute anything. I'm going to substitute in negative 3. So the absolute value of negative 3 is 3, right? And then divided by 3 is 1. So I'd go to negative 1, negative 3, negative 1. And so that's why it's going to end up like that. It's useful, not for us. It's not going to be useful for what we do, but it is useful in calculus for some stuff. So again, just kind of want to expose you to it. Another way to write that function is SGN of x, meaning signum of x. And it's written as a piecewise function. If you were not in pre-AP Algebra 2 last year, you may not have seen piecewise functions. Even if you were, you may not be super comfortable with them. It's okay. I'm just going to write it down. We will talk about piecewise functions, and I'll kind of reteach some of that stuff. But again, don't let this freak you out. So signum of x, to write a piecewise function, you have to have a little bracket because all of this is happening here. So signum of x equals negative 1 when x is less than 0. It equals 0 when x is 0. And it equals a positive 1 when x is greater than 0. So that's that written as a piecewise function. Okay? So you can actually get that 0 in there. It does. Your anchor points are basically 0, 1, 0, 0, and 0, negative 1. But you have to know that these are open circles here. Does that make sense? So if you can get that done, and then you just draw it out, and that's it. It's that easy. Okay. All right. What other questions do you have? All right. So on the test, because on the review that I gave you, it does not have anything about parent functions. All I'm going to expect you to do on the test is maybe sketch some parent functions. And there is a difference between sketching and graphing. Graphing means I'm going to go actually plot points. I need either a grid or I got to make hash marks. Sketching is showing me you understand the general shape. So I might have some little x and y axis that looks like this. And I say, okay, I want you to sketch for me a cubic function. So you're going to do this. You're not making hash marks. You're not doing anything. You're showing me you know the shape. Okay? I want you to sketch for me an absolute value function. It looks like this, right? You don't even necessarily have to use a straight edge. You just kind of have to make it look straight. We're not plotting points. I don't care about the anchor points on the test. Just a sketch so I know you know the shape. Make sense? If there happens to be asymptotes, like if I said the reciprocal, then you would draw in the asymptotes, and do this. Right now, for this test, that's all I care about is that you actually know what they are and what they look like, okay? We'll get to the rest. Right? Then also as we go through these, because we're going to spend quite a while on these, you're going to have to actually show me with your arms, so we're going to do that in just a little bit, but I'm going to stop the video. So make sure you go through, even though these are notes, you have to go through and finish everything, okay? And I will come around and help you if you have questions. I'll double check that you're right, but you should hopefully be able to think through this stuff and get it filled in, okay? Are we good? Awesome.